Economics of ECM. Fixed costs of ECM installations are quite high as compared to its operating costs. Overhead costs are the same as for other convention methods. Some costs are unique, such as those of high power electrode tooling and electrolyte. Electrode or tooling cost is a fixed cost because there is a little wear of the ECM tool. There occurs, however, a negligible abrasion wear of electrode due to electrolyte flow across the gap. Electrolyte is not as costly as one might think it to be. The most widely used electrolyte is sodium chloride and it is quite cheap. ECM installation need not be operated by very skilled engineers and the operation of the machinery can be learnt easily. The economic success of ECM in fact depends largely on the choice of applications. If an operation is simple or if the material can be easily machined by other methods, the high cost of ECM plant cannot be justified. Applications of ECM. Electrochemical turning. The figure shows a typical setup for an ECM turning operation. Here the tool is made as wide as possible to cover the intended area. The tool can also be made to any required complex shape. Holes are provided in the end of the tool to supply the electrolyte. The tool is fed into the workpiece in the same way as in conventional machining. The electrical and other parameters are the same as in ECM. Special equipment are available for both face and peripheral metal removal. Electrochemical honing. Electrochemical honing can be used to increase the material removal rate by a factor of 2 or 3 than that achieved in conventional honing. Conventional abrasive honing stones are used to maintain precise size of the bore. As with conventional ECM, the workpiece is the anode and a stainless steel tool is the cathode. The ECM tool consists of a hollow stainless steel body that has expandable non-conductive honing stones protruding from at least 3 locations around the circumference. The honing stones are mounted in the tool body with a spring-loaded mechanism so that each of the stones exerts equal pressure against the workpiece. Material of any hardness can be machined by ECH as long as it is electrically conductive. The advantage of this process are increased material removal rate, burr-free action, less pressure required between stones and workpiece, reduced noise and reduced distortion in thin-walled components. ECH equipments are available usually for internal honing applications. Electrochemical grinding. In electrochemical grinding, the metal bonded grinding wheel impregnated with diamond abrasive is made the cathode and the workpiece the anode as in ECM. The electrolyte, which is usually sodium nitrite with a concentration of 150 to 300 grams per liter of water, is welded through nozzles into the wheel rather than the work and the wheel is submerged. Though the basic operating principles of ECG and ECM are the same, there are differences in applications and methods of functioning. Whereas in ECM, the tool never touches the workpiece. In ECG, the metal bonded grinding wheel lightly touches the workpiece. The metal removal is largely brought about by electrochemical action and only 10% of volume of material is removed by abrasive action wheel. Therefore, the pressure between the wheel and the workpiece is only about 10% of the conventional grinding process, enabling fragile materials to be ground. Electrochemical deburring. Electrochemical deburring is a process for the removal of metal burrs by anodic dissolution, the same principle as ECM. Electrochemical deburring is used exclusively to deburr all radius workpieces. ECD differs from ECM in that the electrolyte pressure, electrolyte flow and current are all relatively low. Another major difference is that the cathode tool is usually held stationary in ECD. ECD process has been successfully applied in many different industries ranging from consumer appliances and automotive to biomedical and aerospace products. ECD process is used in automotive industry for deburring and radializing the cast holes in crankshafts. ECD should be applied to selectively deburr small areas or areas that are impossible to access by other means.